Hello and welcome to my presentation about our work coined Localization Prevention of Satellite Internet Users. And this work was done with my colleagues from the System Security Lab of the Technical University of Darmstadt. Satellite internet has started to play an important role in conflict zones, and the conflict in Ukraine has shown this, as the US government has recognized the importance of a free flow of information and has funded the widespread deployment of Starlink. In a few months, Starlink has reached over 150,000 active users in Ukraine for the population to stay connected even with the impaired communication infrastructure. As a response to this significant increase in users, Starlink became target and experienced a wide range of jamming attacks, which were unsuccessful. However, an unfortunate trend in the conflict also led to the UN issuing warnings to journalists as they may be targeted and in danger. After the widespread deployment of Starlink, a security researcher issued a warning on Twitter stating that Starlink users may become potential beacons for attacks due to triangulation of their signals by other satellites. The CEO of Starlink promptly reacted to this information by issuing a warning to all Starlink users as they may become targets. Tracing satellite signals to target particular people also has an unfortunate precedent with the killing of Marie Colvin, a famous journalist who has allegedly traced via her satellite phone. Thus, any Starlink user that wants to upload incriminating data, such as a photo over a satellite internet connection, exposes themselves to triangulation attacks, as the gateways basically act as beacons sending radio waves. Base stations, such as the one from Starlink, provide a Wi-Fi network in the vicinity of the base station, implying that users of this network connection are in its vicinity. So this brings us to our research questions on how can location privacy be guaranteed in this scenario. First, we provide some background info on the related work regarding the related topics, which are emergency communication networks and approaches providing location privacy in mesh networks. Recent works in emergency communication networks utilize unmanned aerial vehicles, also called UAVs, or heavy-duty vehicles such as helicopters to provide communication services to a disaster network. However, due to their nature, they are only applicable for short-term disasters, for short-term disaster relief. Location privacy in mesh networks can be accomplished by technologies like phantom routing or network coding, which unfortunately have impractical adversarial models, such as for network coding, for example, the attacker must be unknowing of the technology being used in the first place. Fake traffic and pseudonymity approaches exhibit an impractical network overhead, as for example, fake traffic floods the network and decreasing its throughput while aiming to distract the attacker. In addition, overlay networks such as Tor assume a fully connected network and are therefore not applicable. Therefore, we introduce our approach coined AnonSat, which does not rely on custom protocols or pre-installed apps, prevents localization of its users, and builds on top of off-the-shelf hardware. AnonSat achieves these features by equipping every base station with a long-range radio which spans a mesh network over all base stations. A user can connect his device through Wi-Fi out of the box with the base station, but the base station does not forward the data directly to the satellite, but routes it randomly through the network. In addition, the network regularly switches to a different output gateway to prevent localization over time, adhering to the maximum amount of allowed hops. We implemented and evaluated a proof of concept based on Raspberry Pis and LoRa long-range radio modules connected to a Starlink base station. We have chosen to use sub-gigahertz LoRa because it uses unlicensed frequency bands. To send IP packets over LoRa, we utilize the open source software TNC Attach, which creates and sets up network interfaces to translate IP to LoRa and back. Unfortunately, the implementation has no support for packet fragmentation and reassembly, and therefore only utilizes the maximum LoRa packet size. To speed up the translation, Between Ethernet and LoRa, we added simple fragmentation support to TNC attach. For example, Raspberry Pi 1 sets up a Wi-Fi access point and forwards all packages to the LoRa interface utilizing NAT until Raspberry Pi 3, which then forwards them to the Starlink router connected via Ethernet. As the origin gateway, Raspberry Pi 1 is in charge of setting up routes for the client's traffic to keep track of the duration of each link. If a connection is kept alive for too long, the origin gateway creates a TCP packet with a set RST flag and injects it into the packet flow in both directions, killing the connection. Afterwards, the origin can establish a new route for this client. Now I will present some excerpt of our considerations and evaluation. For the full evaluation, consider reading into our paper. One technical consideration we had was the selection of the radio technology. For the maximum data rate, we also considered alternatives like the fast long-range communication FLRC for LoRa 2.4 GHz, which uses demodulation and error correction techniques for a significantly improved data rate. However, the current implementation of this is not practical for our use case. Further, the last column, as you can see here on the right on the table, shows if the respective technology uses unlicensed frequency band. For example, LoRa supports a variety of different sub-gigahertz bands which are publicly usable in the respective region. For example, North America allocates different bands than Europe. While the other technologies are licensed bands, we expect that legal restrictions play a lesser role in the settings applicable to Anonsat. Here I will present now one example of our security features. One problem with longer connection sessions is that over time, an adversary can geolocate the user by triangulating output gateways over time. If a user always uses gateways 3 hops away from him, an attacker can draw a circle around all the gateways used, and the center of the circle then may be the location of the user. Therefore, we introduce a selection bias for the output gateways. For each client, the origin gateway will generate a random direction and weight bias. This way, the centroid of the circle shifts to a random location, such as the output gateways, and thus the user cannot be used to trace the origin anymore. As there are no public datasets for our use case, we collected public Wi-Fi and Wi-Fi mesh network node location datasets from different sources, such as Freifunk. As you can see, we found datasets all over the world with up to 5,441 nodes per dataset. Here in detail, we show a geographic distribution of the dataset of New York and Hong Kong. We utilize these datasets to conduct a large-scale simulation-based evaluation. Here, I will now present you the network simulation with an increasing number of users. And for this presentation, I give these example parameters: 5 kilometer range per terminal, 166 kilobyte per second max local throughput, a maximum of 3 hops, and each user tries to send 200 kilobyte of data over TCP/IP, which is around the size of a photo on social media. Also, 5 kilometer and 166 kilobit per second is around the data rate of a medium LoRa implementation. So here on the right, you can see that when the number of clients increases, the average time to send 200 kilobytes in second increases logarithmically, which is around 50 seconds for 30 number of clients. This is true for all datasets except for Paris, which is an outlier as it has a bottleneck node connecting 2 subnetworks. Basically, in this scenario, it would be better for the throughput to use these 2 subnetworks as independent networks and don't connect them using the bottleneck node, as the bottleneck node slows down the throughput. We also evaluated the distance metric to evaluate the key security parameter max hops. we measured the average distance from the client's gateway, the origin, to the output gateway. We employed a simplified simulation over our data sets to get a large sample size of 10,000. We used 1 to 5 kilometer range per terminal and 2 to 10 hops. For each sample, we selected a random origin with a random output gateway less than max hops away and measured the actual distance from the origin via their geographic position. Further, we executed this simulation with different max hops, as I said earlier, 2 to 10. And as you can see here, Linz and Adelaide are confined. Even 2 hops is enough to reach the maximum distance, but wide-ranging data sets in terms of the overall covered area by nodes, like for example Hong Kong and Rhein-Neckar, show a nearly linear increase in the distance with an increase of max hops. Now we come to the TLS setup evaluation. As most internet services today are based on TLS sessions, this is a more practical number than measuring just simple round-trip delays, especially as we want to see the effect of concurrent data transfers and session establishments in the network. And with a range of 5 kilometers, the 2 data sets here on the right, Adelaide and Linz, show a much better performance due to all the nodes being packed closely together in the small area. But note that this is an implicit trade-off, as the low average distance between nodes naturally also affects the distance to origin, which I presented in the last slide. So now we also, I will also show you an example what we evaluated on the security guarantees. We evaluated the so-called anonymity set metric as defined by Chaum, and which is basically the set of parties from which one is not distinguishable when using our approach. And here on the in the table on the left, you can see for 5 kilometer range nodes, the average anonymity set size, for example, for Hong Kong is around 417, which means a user is indistinguishable from 417 other users in this network. We also evaluated the effective set size as proposed by Zeriantov et al. And this basically means the reachability of each node throughout the graph, where you can see is basically 278 for Hong Kong. We also calculated the average number of paths between any 2 gateways, which should imply the general connectivity among the nodes in the network, and we calculated the unique path between any 2 nodes, which implies the reliability when individual gateways fail, because the data can take another route to this goal node. We also measured the round trip time on our proof of concept implementation using a standard ping via 0, 1, and 2 LoRa hops to a server on the internet through the Starlink connection. Please note that using Starlink alone already adds around 50 milliseconds of delay or more. And we sent 100 pings and averaged the results, as you can see here on the right. We have a very low packet loss from 0 to 4%, and a round trip time for 50 milliseconds for 0 hops to 211 milliseconds to 2 hops. We also implemented our own API service to upload images using REST over TLS using HTTP2. We used a post request to upload a picture of the size between 50 kilobyte and 200 kilobyte, which is also the average size of images used in social networks and, for example, WhatsApp or Skype. And as you can see here on the right, we sent image sizes, uploading them and downloading them in both directions, and it takes between 60 seconds and 276 seconds for the biggest picture. Thank you very much.